Today I'm going to tell you about our work in non-transition metal chemistry, but it's the same idea of how do you craft chiral space. If you think about asymmetric catalysis, the thing that we learn from biological mechanisms for asymmetric catalysis is that it is chiral space and how that imposes itself on the way molecules present themselves for chemical reaction that is responsible for the excellent and anti-selectivity that we see. And as synthetic chemists, a way to address that problem should be doing the same thing. It's how can we create chiral space? And we became interested in this not only in transition metals, but beyond transition metals to the more traditional types of non-transition metal catalysts. And the reaction that set us off, as it set a lot of other people off, was the Aldol reaction. As I frequently discuss when I'm talking about synthetic chemistry, there are two challenges for synthetic chemistry. The first challenge, which is the one that seems to be front and center, especially in academics, is the challenge of how do you make reactions more efficient, more chemo, more regio, more diastereo, more enantioselective. But there is another challenge that we cannot ignore, and that challenge is how atom economic are our reactions. The Mitsunobu reaction is a reaction you should not use. The problem with the Mitsunobu reaction, it works. And because it works, you use it. But you shouldn't. Now, what we need is a better way. And that is yet to be discovered. The Vidiq reaction, Nobel Prize winning reaction. It's a terrible reaction from the point of view of atom economy. You have transfer of molecular weight 14 and you throw away nearly 400 in molecular weight as a waste product of that reaction. It's a wonderful process. It solved the problem of regioselectivity, but it's not a good solution when we realize you can't generate 10 times more waste or 20 times more waste than product that you want. That's not the way synthetic chemistry should be performed. And the Aldol reaction is a classical reaction of something that can indeed be an ideal reaction. It can be A plus B equals C, where anything else is being used catalytically. And when we began this work, like a lot of other people also, there was wonderful studies on the power of increasing the selectivity, especially the diastereo and anti-selectivity of the Aldol reaction, but not practiced in the way that the Aldol reaction should be best practiced. And that is simply taking an aldehyde, a donor, and do a simple addition, and to do that chemoselectively, regioselectively, diastereoselectively, and antioselectively. Now, a lot of organocatalysis is the way that people have done some very beautiful asymmetric aldol chemistry in the ideal way. We approached it in a somewhat different fashion. We approached it from the concept of learning from Don Cram, who pointed out that molecular recognition by chiral crown complexes could be exquisite. You could get 14 powers of 10 differential recognition. And how could one use the power of that chiral recognition to perhaps catalyze a process? And one of the difficulties with the work that Professor Cram did was that it didn't evolve to many catalytic asymmetric processes. So we were wondering whether the binding constants being so strong in the crown compounds, it doesn't allow, for example, for catalytic activity. They're mainly meant to bind and hold rather than to release. So we simply said, well, probably we could do something if we would, for example, not have all of the pre-structure of a crown compound, but to have a hemi-crown compound. And you could imagine a structure of this kind where you could have some metal coordinating with these basic sites. It potentially could be a dinuclear species. You could perhaps have two metals coordinating. And this particular one is even more attractive because if you think about chemical reactions, it's A plus B equals C. And what might interact with A preferentially may not be the same that what would interact with B. So maybe a dinuclear rather than a mononuclear catalyst could have advantages. And so the notion might be, could we, because of the nature of this crown, be able to self-assemble a dinuclear complex, and furthermore, potentially even perhaps have those two not necessarily be the same. And what attracted us to this kind of design was also the potential for ease of synthesis. That if you think about how you might make compounds like this, you go back to the Vidiq reaction. You simply carry out a phenol with formaldehyde and amino alcohol, and in one step, you potentially can make these compounds. And that is something that's also of concern. You don't want to have a 20-step synthesis to make a catalyst. You'd like to be able to have it be as simple as possible, but at the same time, allow you to assemble a variety of different structures in order to learn more about how you want to design that chiral space. And what we did show when we were doing this chemistry were that these types of unconstrained amino alcohols, when they would form complexes, and the metal we chose was zinc as the metal, in part that came from the fact that many aldolases are based on zinc. And we found that these, in fact, did not give very nice results. But when we introduced an additional constraint in the form of this 5-membered ring, things changed significantly. Now, these complexes can be easily made by starting with this bromide, this dibromide, which we generate with formaldehyde and HBr. And using that, it makes it easier to do variabilities so that we can then just take this compound already pre-organized and take a pyrrolidine and substitute. And now, depending on what you want for your alcohols, you could add organometallics to those esters, and you would therefore have the hemicrown compounds that I was alluding to. Alternatively, we can preform the proline with these groups already in place and then do a substitution reaction. So by using this strategy, it would allow us to do variations in especially the nature of this part of the molecule, because as you will see, that is what's going to be responsible for creating the chiral space. And so we believed that being able to systematically vary that, we might learn what are the factors, structural factors, that gives us the optimal results. The idea was also perhaps putting groups on this side of the molecule to reinforce that stereochemistry. And so we wanted to also have access to being able to vary this side of the molecule. And this, again, is very readily achievable simply starting with ketoglutamic acid. If you take ketoglutamic acid and you reduce it to the aminol, and then you do an addition, it occurs from the less hindered face. That gives you the nice trans compound, and then you treat that with an Arrow-Grignard reagent, and you could obtain that prolinol. Alternatively, if you want these two groups cis, you undergo the addition of the Grignard first, and then you do a reduction, a deoxygenation with a silane. That hydrogen comes in again trans to that ester, so it puts these two groups cis, and then, of course, you have access to the opposite diastereomer. So we can have a great deal of control in building the chiral space as we construct the different pyrrolidines, and this is a relatively straightforward process. It was very nice that some years after we've done our work, our initial work, there was a group in China, in Shanghai, who was able to crystallize our dinuclear zinc complexes, having this paranitrophenolide allowed them to crystallize that. And they indeed obtained a X-ray structure, which I can also say that it is very close to what we had projected. We did do some preliminary study at the Stanford Linear Accelerator where we could determine in our complexes that the internuclear distance between the two zincs was around 3.2 angstroms, and that's almost the ideal that you want. And indeed, that was virtually identical to what was observed in the X-ray structure as well. So the verification that these two zincs are in a very good orientation. It's also important to point out that in this crystal, they were bound to a solvent molecule, one on each side of the zinc, and that the chiral space, as I'm trying to allude a little bit in the nature of these aromatic rings, is indeed going to influence how things can coordinate and thereby affect the chemical reactivity. And by and large, using this model, which is a angular, or let's say this phenyl ring sticking straight at you, this phenyl ring being in the plane, and the reverse situation over here, one phenyl ring being perpendicular in the back, this being in plane, that leads us to be able to predict that if we consider one of these zincs as the Bronsted base site and the other as the Bronsted acid, or the Lewis acid site, that you would have this type of orientation, and so you would have the Lewis or the acidic site interacting with this basic one, and you have the basic site of the reactants interacting with that acidic one. And this would allow us to predict the absolute configuration of the reaction. And indeed, we could show you could carry out the formation of these zinc complexes, that you could take a methyl ketone and indeed have generated the enolate from the methyl ketone in situ, the other zinc coordinating the aldehyde. This then sets the stage for this approach where this is in the front, this is in the back, giving rise to that stereochemistry, liberating that zinc to coordinate another molecule of the carbonyl compound. That's setting the stage for enolization, this picking off that proton, generating the product, giving back the intermediate, and you have a very nice catalytic cycle. And one of the things that we can show that does differentiate this approach to many of the others is the reaction where you take MVK as a donor. If you think about the Aldol reaction, one thing you don't see is the use of MVK as a donor in the Aldol reaction. It's because it does itself in. But we can employ MVK. We have to use excess MVK, but we can employ MVK in a reaction and obtain 63% yield, 94% EE in generating that product. You do have an interesting effect when we take this aldehyde in the presence of a weak acid, isopropanol. We get a modest yield, excellent EE of the adduct. Given the availability of your starting materials, because it's the MVK that's in excess, not the aldehyde. So this can in fact be a very reasonable reaction. However, if we don't have isopropanol present, we get a very interesting product instead. We get this pyran, which is actually a 2-to-1 adduct. What has happened is that the intermediate, instead of being protonated, it's captured by a separate second molecule of the MVK. This now generates a new enolate, which does an intramolecular aldol reaction. And you have a very nice way of getting this kind of 2-to-1 substitution, 67% yield, 99% EE. You've created a lot of molecular complexity in a single event with near perfect enantioselectivity. Now, the point of this is that it is a nice juxtaposition of functionality that emerges by being able to use MVK. You have an alcohol, you have a ketone, you have a double bond. So you can use the alcohol to direct the stereochemistry of reduction of that carbonyl to generate this diol. You can use the stereochemistry of the allylic alcohol to direct a 1,3 dipolar cycloaddition, and that now creates a potential hydroxyamine derivative where this stereochemistry is induced with high selectivity as well. So we have generated then in a very simple protocol a degree of structural complexity where you have excellent DR and EE in acyclic stereochemistry. Alternatively, you can obtain the anti-product, again by selective reduction with the acetoxyboranes, and then again do the cycloadditions, and in this way you can selectively modify the stereochemistry of the remaining centers. So you have a lot of flexibility by being able to do this reaction. The success of vinyl ketone induced us to think about acetylenic ketones, because acetylenes are a family of compounds, or as a functionality, I should say, functional group, which has very great potential in organic synthesis because they are particularly prone to be substrates for catalytic, especially transition metal reactions. And those reactions can be highly chemoselective. So we were interested in knowing, could this extend over to alkynyl methyl ketones? And the answer is yes, it can. You can very nicely obtain the desired, product. What did I do? 75, 85% yield, essentially enantiomer pure. You can take this alternative, instead of having an allyl group, you can have this hydroxy alkyl group. And the one thing that was particularly intriguing to us was that although in our Aldol reaction, as you will see, we could only have one carbon adjacent to the carbonyl group. We could have some other groups on there, but it can't be another carbon. But with the alkynyl ketones, we now, for the first time, could also take an alkyl group on that methyl group and be able to perform the reaction with a decent level of DR and a decent level of enantioselectivity. So this looks like it can now allow us to expand the scope to a broader range of ketones. And do remember that acetylene is, by hydrogenation, a saturated alkyl. By semihydrogenation, it can be a cis double bond, a trans double bond. And by a variety of transition metals reactions, it could be a lot of other things as well. So this gives us, we think, particularly a great deal of power in being able to use this methodology for complex molecule synthesis. So take amphotericin as an example, that this part of the molecule could be this unit of the amphotericin system. And so if you take this compound, we can show that that's now accessible from this aldehyde, that methyl ketone, 75% yield, 99% EE. Alternatively, we have a program towards listraduxin, where hopefully we'll be finished in the not too distant future, where we can take this as this unit that's outlined in red. And so again, we have that beta hydroxy ketone, and that we can take this aldehyde, that methyl ketone, 76% yield, 99% EE in generating those chiral centers. And in the synthesis that we have recently completed in losanolide, we can carry out the similar type of intermediate from these two starting materials in 78% yield, 99% EE to give us that beta hydroxy ketone. So these unsaturated types of methyl ketones, we think, are a case where this catalyst system is particularly well suited to carry out such reactions. Now, the class of compounds that one can do very nicely with this, where it's not just a methyl ketone, is when you bear a hydroxyl group. So most recently, we began looking at not ketones, but carboxylic acid derivatives. So building on the fact that N-acylperols in many ways mimic aryl ketones in their chemical behavior. And there's beautiful work that's been done by a number of people, but especially Dave Evans, utilizing acylperols and Shibasaki as well, I should say, as surrogates for phenylketones. Except these have particularly advantages in that it's a pseudo-activated carboxylic acid. You can add amines to generate amides, you can add alcohols to generate esters, and most importantly, you can add Grignard reagents to add and form ketones. So it's a very nice type of group that gives you a lot of structural flexibility in downstream processing. And if you take this hydroxyacylperol and an aldehyde and take the 4-methyl derivative, that's this one, that one can indeed obtain the product in very, very reasonable DR and EE. But we can do better if we put a substituent right there. Instead of having hydrogen, we put an ethyl group. It improves the DR and the EE somewhat. But most importantly, we can also vary it by the nature of the prophenol that we're using. And there is a second type of constraint which I haven't talked about, where by placing substituents in the meta position with respect to the phenol, the steric interactions between that methyl group and the proline would conformationally fix the rotamer of this portion of the molecule. And by that conformational bias, the idea would be that hopefully that would improve our reactivity and selectivity. And indeed, when we do that, we find that this is a generally better system, 11-to-1 DR, 92% EE in carrying out the addition reaction. And this is the best system in general for carrying out these reactions. So not all of these reactions were done with this 3,5-dimethyl, because our initial work was done with the standard system where we just had a methyl group there. So here we're back to this is still the 3,5-dimethyl, 4-to-1 DR, 88% EE. But here is just the 4-methylprophenol. It's this system here where we can do a little bit better in the DR, but still the EE is lower. And all we would need to do is to go to the dimethyl case. We haven't just redone all the examples with the dimethyl that we had already done. But the 3,5-dimethyl has done pretty well in terms of carrying out this reaction, although when we have additional basic sites here, as you can see, we did suffer in the DR in this particular case. And this particular example was looked at in the context of a synthesis of this natural product. This reaction can also show, importantly, control relative to the diastereoselectivity, or what I call catalyst controlled versus substrate control. So in our synthesis of lolimolide, this was an intermediate that we had designed, which we were going to simply make by using a Julia squared olefination reaction. And so we needed access to this particular compound, this dihydroxyalkoxyaldehyde. So what we're going to do is to have a pre-existing stereocenter, and the question is going to be, can we get this as a catalyst-controlled stereochemistry, or will this pre-existing stereochemistry give us a matched-mismatched case? So we took this particular enantiomer of the substrate, doing our addition. Again, this is with the R prime equal hydrogen, and this being TBS. And as you see, 1.5-to-1, no particular selectivity. But when we use the ethyl compound, now we see the DR jump to 4-to-1. So it does make a difference to have that additional geometry or steric bulk on the parole group to give rise to a more reasonable DR. It turns out that it also depends on the nature of the protecting group. And switching from TBS to MOM improves the selectivity to 10-to-1. So one has then a reasonable level of diastereoselectivity, but it's still the question, is this a substrate controlled or catalyst controlled? So what we did was to change that enantiomer to this one and carry out the reaction with the same catalyst. And what we find is that we get the same stereochemistry as in the other case, where these two centers are opposite of each other, with the same level of enantioselectivity favoring this diastereomer. So what that tells us is that this diastereoselectivity that we see in this reaction is independent of the stereochemistry that is already pre-existing in the substrate. So we really do have a catalyst-controlled event, not a substrate-controlled event. And we use this then to complete the synthesis of this unit, which then went on to complete the synthesis of the lolimolide. Could we extend this idea from beta hydroxy compounds, or alpha hydroxy compounds, to alpha amino compounds. There's been a number of investigations dealing with these glycine imines and aldol-like reactions, but the one thing that was not available, at least up to the present time, was a good syn selectivity with good EE and DR. So we wondered whether we would be able to employ these prophenol systems to carry out such reactions. So taking our standard prophenol, we could get a 64% yield, about an 8-to-1 DR, and 81% EE in carrying out that reaction. So here we began looking at the question of modifying the prophenol. And one of the things that we had done was to change the nature of this substituent from a methyl group to a methoxy group, a more donating group. And we did see in the reactions of the aldol variety, simple aldol reaction, in some cases an improvement by having that electron donating group. And as you can see, that carries over to this reaction, but not very much. Just a minor improvement in the reactivity. So we decided to also look at this dimethyl compound, and disappointingly, that restraint made things significantly worse. So we thought we really needed to have a new concept in our catalyst design. So we went away from the phenols to ask what happens if we just make these much bigger. And as you can see, it sort of just is almost unchanged, a little worse than just the standard system. But the thing that made a little bit more of a difference was when we introduced a second stereocenter on the pyrrolidine. And when we put a phenyl group, then we could get slightly better, nearly 90% EE, and about a 10-to-1 DR. And indeed, the phenyl seems to be more or less the ideal. Going to a bulkier group like naphthalene didn't change things very much. 1 naphthalene versus 2 naphthalene, not much difference. And finally, instead of having these fused ring systems, just have extended aromatic systems. Again, not much difference. So it's just this initial phenyl ring, and what we believe is happening is that this ring is interacting with the phenol to once again fix the relative conformation of the pyrrolidine unit with respect to the zinc. That interaction is helping to fix it so that we're improving the rigidity of our chiral space, which gives rise to this improvement in both DR and EE. And this proves to be a rather interesting reaction to a wide range of substrates. Now, one of the things we've done here, and you can also imagine, you could simply work up the reaction by hydrolysis, and that gives you the free amino compound. We chose to work up the reaction with sodium cyanoborohydride to do a selective reduction, because this automatically then puts a benzhydryl group on that nitrogen, which we can use as a nice nitrogen protecting group for carrying out further structural modifications. And then the removal of that by hydrogenolysis occurs quantitatively and very rapidly. So it's a trivial group to remove. So generally, we just chose, instead of to use the hydrolytic workup, which others have already done, we chose to do it by this reduction workup. And we began looking at the ability of putting in sterically bulky groups, as you can see here. And one other thing I should mention is that we are employing here methyl esters. In almost all the previous work using these glycine imines in aldol reactions, one employs T-butyl esters in order to give rise to the selectivity that you require. In this case, we don't need to do that. We use methyl esters. And T-butyl esters also can be employed. There is no benefit of using a T-butyl ester versus a methyl ester. They're both equivalent. So you can have these bulky groups. You can make them a little bit less bulky, and you still obtain good EEs, 88%. Having a linear chain rather than a branch point, you do lose some EE, 73% EE in the linear system. T-butyl esters can work, as I mentioned. So again, so we can compare. And if anything, as you can see here, there's a slight loss, 89% versus 95%. And here we have 94% EE. And in this case, in comparison, we have 91% versus 88%. Within experimental error, those two numbers, I say, are identical. So the methyl esters and T-butyl esters do the same thing. Again, we ask the question, how much of a catalyst-controlled versus substrate-controlled reaction can it be? So if we introduce a stereocenter into the substrates, like this oxygen, will this reaction be influenced by that stereochemistry? So we looked at this compound in which we saw the DR was 9:1. The DR is, this is syn, so it's the DR with respect to that stereocenter. So this is the major diastereomer, and the one corresponds to the one where these two stereocenters are inverted. On the other hand, if we take the opposite stereochemistry there, but the same stereochemistry of the ligand, we see, in fact, if anything, an improvement. So there is a little bit of a match-mismatch case, but in both cases, we do pretty well. That it gives rise, in both the so-called match and mismatch case, diastereoselectivities that are in a synthetically useful vein. The T-butyl esters compared to the methyl esters show a similar trend. So again, one sees about the same change in DR as you have from this to this, but in both cases, by far the major isomer is the catalyst-controlled reaction rather than substrate-controlled reaction. You can take it further to this amino compound, where one sees more or less the same type of event, where you have, again, this 9:1, in this case 13:1 DR. And so what it does mean here, we believe, is the ability of being able to do acyclic stereocontrol in catalyst-controlled chemistry using otherwise the identical conditions. And once more, you can have additional functionality like another ester. And this, again, 88% yield, 9:1 DR. So we think this is a reasonable approach to give you these polyfunctional amino acids in a very simple fashion. And by far, of the ones reported to date, these have been the highest selectivities that have been seen for the syn diastereomers. A class of aldol donors that has not had a lot of attention are these alpha Daizo esters. Yet they can be, under basic conditions with things like DBU, affect aldol additions to aldehydes. And we wondered whether this particular motif might be differential because of the juxtaposition of the two metals, not simply giving an enolate, but giving a cyclic derivative where you'd have the C-bound metal carbon bond in addition to an O-bound in a Lewis acid-Lewis base interaction. So this could be bidentate coordinated to the two zincs. The distances are ideal for that type of arrangement. And in doing that, would that then translate into better control of the stereochemistry of the addition step to give you the adduct? And then again, of course, this would react with starting material, liberate the product, and you nice have a catalytic cycle. So this would be a way of generating beta hydroxy alpha diazo esters. Now, when we first did this work using our standard conditions using zinc, we found we got pretty low enantioselectivities. Forget about the sign for a minute, I'll come back to that. But it was just a low EE in generating the beta hydroxy ester. When we switched from zinc to magnesium, we found that we got some improvement. Now, the difference between these two is nearly 40%, because this is in the opposite stereochemical direction compared to that. That's what the minus means. So there was a significant enhancement in the EE. But one of the problems that this system had, and something I haven't really spoken about, is what is the degree of coordinative unsaturation of the zinc? How many groups can be coordinated to the zinc? And the reason I mention that is that the work we did with our methylalkynyl ketones demonstrated to us that in the additions of that reagent, the methylalkynyl ketones to aldehydes, the product of the reaction influenced the stereochemical course of the reaction. And what we showed was that when we added to the catalyst, prior to adding the substrates, a beta hydroxy ester to serve as a bidentate ligand, that new complex that you're generating in situ gave us very high selectivities, the 99% EEs that I was showing you. What we worried about here was that it wasn't the product, but it was the starting material, that this coordination could be with a second diazo ester. And then, of course, there's an ambiguity of which one's going to form the bond. So what we should do here is to block that additional coordinative unsaturation of the zincs, and we did that by adding a diol. And when we add this diol, the EE jumped to 65%. Now, if our logic that it is the coordination, the high degree of coordination of the diazo compound with the catalyst is correct, we should keep the concentration of the diazo compound low at any given time. So if we simply do a slow addition of the diazo compound to the compound, then you get a 95% EE. And this is by far the highest EE that's ever been seen for the use of diazo esters as donors in aldol chemistry. And it's reasonably general. You can have various substituents on this aromatic ring, chlorine, methoxy. You can put it into various positions. And as you can see, you get around 90% EE, plus or minus. We could take this alpha-beta unsaturated aldehyde and carry out the addition reaction. That in this case, we do see still very good EE, 94% EE. Saturated aldehydes, 97% EE. So it doesn't have to be aromatic aldehydes. Alpha-beta unsaturated aldehydes, saturated alkyl derivatives give rise to your desired products. And there's a very nice reaction that was developed some years ago by a group in Alberta, where you take these alpha diazo compounds, you react them with trialkyl boranes, and they generate these alpha alkylated esters directly. And it turns out when you do it with this compound having this beta stereocenter, that alkylation reaction gives rise to very good diastereoselectivity, where these two groups are syn. So here you have a way of then not only installing that beta hydroxy group, but you can install alpha alkyl groups to the extent that the organoboranes are available. And now you have beta hydroxy alpha alkyl esters coming from a simple diazo ester and an aldehyde. These adducts can also be reductively cleaved, and that just gives you the beta hydroxy ester. But more importantly, they can be oxidized with DMDO. And when you oxidize them, they give you this alpha keto ester. And that stereocenter is not affected. Furthermore, with mild organometallics, you can then add chemoselectively to that ketone. So you can use a reducing agent. This is just a borohydride reducing agent. But you can also use, for example, allyl bromide using a tin 2, not an alkyl tin, a tin 2, and generate this tertiary center 50-to-1 DR, 93% EE. So now you can have alpha beta dihydroxy alpha alkyl esters in a simple two-step or totally three-step process. But it's 2 steps because you don't really do anything to this except add the organometallic to it. To give you one illustration in looking at a target, one could imagine that this portion of these macrolides may be derived from this kind of chemistry where we need to introduce a methyl group into that ketone, and that's going to come from this Daizo compound. So now we take ethyl diazoacetate and we take propanol, and we carry out the addition reaction with the prophenol. We get a 52% yield, 96% EE of that compound. You treat that with DMDO, and now you treat it with dimethyl zinc. And we use an amino alcohol to promote the addition. And turns out what we do use is racemic prophenol as the catalyst. So you take dimethyl zinc, racemic prophenol, and you do the addition reaction diastereoselectively, and you end up with this building block that could lead us into a synthesis of these types of macrolides. Of course, you have alpha diazo compounds. These behave as typical alpha diazo compounds, so you can, in fact, do some of the chemistry. And one of the reactions, I shouldn't say as typical alpha diazo compounds, as alcohols. And one of the interesting reactions is when you form the trichloroimidates of this reaction. Now, a group in Peking University showed that these derivatives were very labile derivatives. And they showed that it did rearrange to generate the corresponding beta-amido compounds. What they didn't know was the stereochemistry of that process. What we could show now is that this process of converting that alcohol to this beta-amido compound can go with good chirality transfer, and it goes with retention of configuration, not inversion of configuration. And we believe it's a simple system here, that it is a system very prone to undergo the alpha elimination, that you have more or less negative charge there that promotes the ionization to give you a tight ion pair, which just then recombines without it reorganizing at nitrogen to give you the thermodynamically more stable amide. So not only do you have access to beta-hydroxy compounds, you also have access to the beta-amido compounds. And the advantage of the beta-amido compounds is that you can see more normal carbene chemistry. The beta-hydroxy compounds, when you start trying to use carbenes, they have a propensity to undergo a 1,2 hydrogen shift. So you get the beta-keto compounds. But when you use the beta-amino compounds in doing this chemistry, then you can do typical carbene chemistry. So you can take this compound, treat it with a rhodium catalyst, and you end up with the product of intramolecular cyclopropionation. Of course, we can take this compound, generate it in the standard way, 92% yield, 95% EE, make the beta-amido compound. And when you take this compound and oxidize it with DMDO, you now have, again, the ability of adding allyl halides in the presence of things like zinc metal, indium-1, samarium-1. In this case, we preferred, instead of the tin-2, the use of zinc. Alternatively, if we do this with cyclohexane rather than phenyl, and we generate the corresponding beta-amido compound, and now we subject this to rhodium chemistry, what you see is CH insertion to generate that cyclopropane. If you don't have the constrained ring of that 6-membered ring, if we have an unconstrained alkyl chain, instead of a 1,3 insertion reaction, what you're going to see is a 1,5 insertion to generate the 5-membered ring. So we have access to all this type of carbene chemistry where the stereochemistry of these events are all dictated by that amido compound. So now we have beta-hydroxy compounds, beta-amido compounds, and you can make cyclopropanes, cyclopentanes, or these alpha-alpha disubstituted compounds. Michael additions using butenolide and nitroalkanes. One can again use that model that I showed you at the beginning, coordination of the donor in the front, the acceptor in the back, giving rise to this adduct with that stereochemistry, and that one has rise to the desired products. And so one can see that you can use a variety of different substituted derivatives, and in the case of this chloro compound, we could get an X-ray structure. So we know what the absolute configuration of these two centers are. You don't have to use the corresponding phenyl. We can use naphthalene rings, and again, still get good DRs and EEs, 94% EE. Instead of using benzenoid type systems, we can use heterocycles, either thiophene or furan, and still get good levels of enantioselectivity. And finally, instead of being alpha substituted, it can be beta substituted, still good DRs and EEs in generating the desired product. So Michael additions is another class of reactions that one can do very well. And here we have really one of the most surprising results in this whole series, is taking these two reactants. It's not surprising they will undergo simple Michael addition. Enolization of that is very facile, and it does a facile addition there. And of course, the alcohol then reacts with that ester to give the lactone. But what's really peculiar is that if we use the standard propanol with phenyl, we get a 9.2 to 1 DR, 96% EE. But if we simply take the same species, but instead of having phenyl, we put naphthol where those phenols are, look what happens. The stereochemistry inverts. You've changed the chiral space to such a point that now it inverted the absolute configuration that we see. And we don't have a good explanation for that one. But we think this is a reasonably general approach. The last thing I want to talk about is the addition of alkynes. As I have alluded to numerous times in my lecture, alkynes, we believe, are ideal building blocks for complex molecule synthesis. And so a lot of our total syntheses are built around what I call the alkyne strategy for complex molecule synthesis, because that alkyne functionality provides you a handle to do a lot of molecular transformations. So we were very interested in having an ability of being able to do asymmetric alkyne addition reactions. There are some very nice procedures out there, and the one that I believe is one of the most valuable is the beautiful work coming from the Carrera group, where using these ephedrine-based chiral ligands and using zinc triflate, that one can do pretty nicely in many cases. The problem that one has in that reaction is that a lot of times the reaction is not catalytic, that it has to be done stoichiometrically rather than catalytically. Looking at this process here, we felt that this might be a nice way because it's really juxtaposes the two zinc. The Carrera system undoubtedly involves also a dinuclear zinc species that self-assembles. But this one's more predisposed to do just that. And because of that, we thought that this may be a system that could have more broad catalytic behavior, where the chiral agent could be used catalytically to give rise to that stereocenter. And that we could then build additional structure on that acetylene. And this would be a nice way for us to access an antiocontrol control. So when we take this aldehyde and we carry out the addition reaction, one finds that we do reasonably well. So with the methoxymethyl compound, we get 97% EE. Using the propylate, in this particular case, it did decrease a little bit, but in most cases, actually, we get EEs in excess of 90%. So this is really at the low end of the spectrum. With these alpha-beta unsaturated aldehydes, we had a rather interesting comparison that the standard aldehyde only gave 36% EE. Now, the way that people have frequently addressed this problem when they had these unsaturated aldehydes is to put a substituent in there, and particularly a bromine, to increase the steric bulk and therefore increase the selectivity. And indeed, this does just that. You get 92% EE by taking the bromo compound. But I don't want to do that. If I don't want bromine, I mean, it's nice to have bromine because you can then do cross-coupling chemistry, so it's a nice building block. So it's really nice to know it does the job. But if you don't want bromine, you don't want to put bromine in just to take it out. Could we modify the catalyst? Now, I go back to my comment earlier that these systems, we believe, in part, lose the stereochemical control because they are polyunsaturated. And if we add a non-reactive ligating group, besides these beta-hydroxy esters, or these 1,2-diols, and the one we added here was simply triphenylphosphine oxide. And when you add now just a catalytic amount of triphenylphosphine oxide, so that stuff you're throwing away from your Vidiq olefination, to put it into a bottle, it's a co-catalyst. Let's use it. And now we get 94% EE. So this business of understanding the coordinative unsaturation of your intermediates really is a prime aspect of getting this chemistry to work well. Utilizing this acetal, we get 90% EE. And again, here's a nice example where we go back to the propylate type system, and now you see 95% EE. This is more typical of what we see using this propylate as a donor. It's an excellent donor. And so you have a gamma hydroxy alpha beta unsaturated ester, really a wonderful functionality for further structural elaboration. And one of the most difficult substrates in any kind of aldol reaction is acetaldehyde. Its propensity to self-dimerize under catalytic conditions is very typically what happens. So we wondered, could this process be used where you could even use acetaldehyde as a donor? We know that the utilization is a problem. But could we find a protocol so that it still would be useful? Remember, acetaldehyde is cheap enough that if we needed to use a little bit of an excess, this is not too costly a thing to do, because the acetylene in this case is really going to be the valuable component. So if we take dimethyl zinc and triphenylphosphine oxide, and what we do now is to add the aldehyde slowly to the alkyne. And you sometimes have to add between 1.5 and 2 equivalents of acetaldehyde. But by doing a slow addition of the acetaldehyde to the alkyne, you can get an 85% yield based on the alkyne, 84% EE. Instead of phenylacetylene, using this alkylacetylene, we do lose a little bit in the EE. But by putting an oxygen here, doesn't matter whether it's an acetate, we're at 90%, an ester, we're at 98%. Putting a group here that has some degree of Lewis basicity greatly enhances the enantioselectivity that we see in these reactions. Looking at these types of targets, generation of these butynylides would be ideally suitable for this kind of approach. Now, in earlier work that we had done in my group, we had used this as a building block. And that one takes this with ruthenium and olefins, you do an alkene-alkyne coupling, and then this hydroxy group cyclizes to the butynylide and gives rise to these types of butynylides very nicely. But we made this from the obvious way that you make it. You take the readily available hydroxy ester, and you carry out a conversion of that ester to the acetylene. 4 steps. But now we can take acetaldehyde 1 step and make the same compound. So starting from an optically active starting material is not necessarily the best strategy. A lot of people have the notion if you can buy the chirality, you buy it. Not if it's going to take you 4 steps to do something you can do in 1 step. What you have to do is evaluate what is the best way to get there. And this is by far the best way of getting there. 1 step outdoes 4 steps any day. Well, given rise, I can also point out to you, you're going to say, well, you can make these propargyl alcohols. Just use the very nice Nuyori chemistry. Nuyori chemistry is very nice, but it's not universal. So in another project in a group, we wanted to make this compound, and we looked at the Nuyori hydrogenation. It just didn't work. It's not that it gave poor EE, it just didn't work. This was not a good group. You do it by the addition of this alkyne to an acetaldehyde. You get 69% yield, 95% EE. So the alternative methods, there's always a need for more methods to do things because they don't work universally. And here's an example where one used what seemed to be the most logical way, and it didn't prove to be the best. This diene looked like this would be an ideal example for being able to use the kind of chemistry I'm telling you about. Because these stereocenters are really far apart from each other. You're not going to have this stereocenter tell that stereocenter what to do. So if you're going to be able to introduce those stereocenters, they each have to be self-controlled. And so we're going to need to add something to this dialdehyde. And this dialdehyde, when we look at alpha-beta unsaturated aldehyde, we don't look at olefination chemistry. That's not the way you should do it. We look at redox isomerization, that you can take a propargyl alcohol and using a ruthenium catalyst, and you can take these two hydrogens and move them over to the double bond, to the triple bond, and you end up with the alpha-beta unsaturated aldehyde. So we simply isomerize that to give you that. And then we're going to do addition reactions of that to give us that. A series of very nice, reasonably atom economic processes. Now to get here, what we are going to do is a Sonic-Ashiri cross-coupling with this diene. As it says, 73% yield. The redox isomerization gives you the bis-enal, 71% EE. And now you can use either the propylate or this trimethylsiloacetylene. I happen to like the propylate system, 84% yield, 99% EE. And when you just hydrolyze the ester and add copper to it, it decarboxylates spontaneously, and you end up with the acetylene. So you have a very short synthesis of this molecule from readily available starting materials based on the combination of the ruthenium chemistry plus the asymmetric prophenol chemistry. Ester scanalide is another area of interest. And having either isomer, that's why I have the wiggly line there. One is ester scanalide C and the other one is D. We envisioned that you might be able to use an Aldol reaction to make a medium-sized ring. The problem now, however, is polymerization. Now, when you're trying to form macrocycle rings, there's been work done where you can form a macrocyclic ring and get some reasonable yields of the Aldol reaction. But when you're talking about medium-sized rings, that's a different matter. You can't take that ketoaldehyde and do an Aldol reaction. So this we used a different kind of chemistry in my laboratories, and that is use a surrogate. We want the aldol condensation. So we don't have to have a beta hydroxycarbonyl. We just be able to introduce a double bond. And we like sulfur. And what we like is that if you take a thioacetal with DMTSF, dimethylmethylthiosulfonium tetrafluoroborate, it's a way of being able to generate a super reactive carbonyl group. And so we could generate that super reactive carbonyl group, which won't do an intermolecular reaction because we're going to have this as an enol silane, that this then could be trapped, and this would give us access to that species. And so what we need is a way of making that aldehyde, and we're going to make this aldehyde by using this ruthenium catalyzed alkene-alkyne coupling reaction using the CP ruthenium triacetonitride. And that would give rise to this species because the double bond here is an enol and it would tautomerize to the aldehyde. So alloalcohol will react with that in ruthenium to give you that. And so all we need then is access to this aldehyde, which means methylpropylate plus this ketoaldehyde, and that works very nicely, giving us 77% yield, 86% EE in generating that beta hydroxy compound. And now using alloalcohol and using this catalyst, you can then carry out the cyclization, the formation of this species. We make the thioacetal. Whoops. We make the thioacetal and the enol siloether, and this cyclizes. We can eliminate, and we have a way of generating Esters camelite. So we have a very short, direct way to this medium-sized ring compound, taking advantage of the alkene-alkyne coupling reaction, the thioacetal chemistry, and it all starts with the propanol addition. This is another example which nicely illustrates the utility of some of these ruthenium catalyzed reactions, but again, the ability of adding propylate asymmetrically to aldehydes. So one wants to carry out this kind of addition reaction to that aldehyde, and this can be done by, again, another addition. So this stereocenter can come from this acetylynic carbonyl. And so what we're going to do is to take this aldehyde, that acetylene, and using the propanol system, this one, that would then promote the addition of that to this carbonyl to give us that stereocenter. Hydrosilation of this triple bond followed by reduction of that gives us this compound. Now we do a second propanol chemistry to add this propylate with that ligand to give rise to this stereochemistry. And then we can do the completion of the synthesis. So as you can see, this was 87% yield, 19-to-1 DR. This is 72% yield, 5.2-to-1 DR to introduce those stereocenters and complete a synthesis of that final target. Just quickly, talk about just two aspects of the same problem. This was a sorafin synthesis that we were engaged in. And what we were looking at is how to make a system like this, where you have two stereocenters, two oxygen stereocenters quite distant from one another. And what we did is to install a triple bond here, with the notion being that our propanol chemistry allows us to take that alkyne and add it to that aldehyde. Now, that reaction also allows us to keep in mind that this acetylene, instead of being there, could be over here, over one. In which case then, because if you look at a diol like this, what's available is glycerol, this epoxide asymmetrically. And we could use the alkyne to open up the epoxide to give rise to that diol. What we need then is to move this triple bond to the terminus in order to do the asymmetric addition. And indeed, one can do the very nice acetylene addition to open up the epoxide, do the zipper reaction under the conditions described by Charlie Brown, which is using kappa, that's 1,3-diaminopropane and potassium hydride. And now you take this, you take the propanol system, 87% yield, 93% EE in generating that stereocenter. And this was taken on to give rise to the final product. What I'm showing you here is simply saying that you can take and use a propyne as a functional equivalent of a 1,3-propyl dianion. And furthermore, the number of carbons in between the dianion can be whatever you want it to be. Any alkyne can be then a functional equivalent of a 1-omega dianion. So let's take in the last example. We were looking at this part of this molecule, and looking at that part of the molecule, we wanted to use 10 carbons in between, 11 carbons in between the dianion. So you're simply going to take, to make this piece. So we're going to have ability of generating this unit. And that's going to come from furfuraldehyde, because oxidation of that aldehyde, of that furan, gives us a carboxylic acid. And so that's the carbonyl group from furfuraldehyde. So we have our dihydroxy compound. So we're going to be doing an asymmetric addition to furfuraldehyde. And this stereocenter is going to come from this acetylene, which in turn comes from the opening of the epoxide with this acetylene. So we take that commercially available epoxide, we open up that epoxide with this acetylene. it gives rise to the the formation of our desired adduct. In the standard way, you complex it with BF3, butyllithium, 92% yield. We take this and run the kappa reaction with it to zip that down that chain, 76% yield to the new terminal acetylene, and finally, we can do the prophenol chemistry using TPPPO, and that gives rise to this adduct. And then hydrogenation of that triple bond gives you that saturated chain. We actually use diimide to do the reduction, and we can go on to generate these two compounds. We have not done the condensation reaction. We're ending up at this point, at this stage in our synthesis. Well, the last technical slide is to simply say that everything we've done with monoacetylenes, we can use for diacetylenes, that we can take diines, and they add also asymmetrically in the presence of triphenylphosphine oxide to generate these stereocenters. 86% EE, 92% EE in doing these additions. And this then could be cleaved and then added to the epoxide, and so you have a very nice way to generate these diene products. And these are an interesting class of natural products that have been exploited because of their anti-tumor properties. So one can take and generate this species by doing an asymmetric addition of the diene, and as I mentioned, having a basic site at this center makes that addition reaction particularly efficient. And indeed, if we use the SS ligand, triphenylphosphine oxide, 90% yield, 87% EE in generating that species. And I show you this example again because you want to know, is this differential from other methods? And I mentioned the beautiful work of Carrera, and he has done virtually the same addition reaction. Here it is. But in order to do this addition, for reasons that are not clear, he had to use 4 equivalents of N-methylephedrine and 4 equivalents of zinc triflate in order to have that reaction. That's one of the problems that does exist in that approach. How catalytic can it be? And in this case, it has to be super stoichiometric, where we still are using a little more than we typically use, which is 10 mole percent, 20 mole percent. I should mention that the prophenol is fully recoverable. You can just precipitate it in the end and recover the prophenol. It's not something you need to throw away. Well, with that, I hope I showed you that this ligand design for main group elements, so far zinc and magnesium, looks like it's a very useful design for carrying out reactions that are catalyzed by acids and bases. And given that so far, this is a range of some of the reactions that we've performed using this kind of a method. And finally, I just sit back and enjoy what is being done by the great group of people who worked in my laboratories. This is a group of the individuals who are mainly responsible for the work I've talked about so far, beginning with Vince. He is a postdoc who was involved in the diene chemistry, Rajiv, and the sorafin total synthesis. Pascal, who's involved in some of the methodology. He's an undergraduate. Dan Fedrick, who did some of the alkynyl methyl ketone addition. Julian, who did the asymmetric conjugate additions using the butanolides. Tom Hunter, who did the work on the methyl alkynyl ketones and the ethyl alkynyl ketone. Suzanne Malhotra, who did the work on the alpha Daizo compounds. Fred, who did the glycine imine derivatives. Chris, who did some Michael additions of reactions. I actually didn't show you the work that he did. Sungkun, who was the one who did work with MVK, and Andrew Weiss, who was a graduate student, was involved in carrying out some of these total syntheses that I pointed out, especially of that diene natural product. Well, with that, it behooves me to say that we are able to function because we've had some generous support. And I'd like to once again thank the departments to come here and share the story with you. It's been a great day. I've enjoyed discussions with many of you people here today, and hope that you can look at this as a way to help you solve your problems. Thank you.